Okay, good morning, everyone. Today we are going to talk about sputtering, another type of physical vapor deposition. So here we have a figure. This shows the basic schematic of our simple parallel plate sputtering system. So it looks like our reactive ion etching system. There are some differences. So in this system, we have our cathode. So cathode, here we have the wafer, target wafers. And then here we should have, for example, aluminum target. And here we have plasma. So we have our pressure difference, our voltage difference between a plasma and a target. And target should be cathode with our lower voltage than the plasma. So the ions will travel to this target. Yeah. And then there will be sputtering happen. And then we have aluminum atoms deposited onto this wafer on the wafer substrate. So the cathode and anode has a very small space, for example, less than 10 centimeters. So in this way, we can improve the efficiency of deposition. So we hope that all the aluminum atoms can be deposited onto this wafer, for example, silicon wafer. And we mentioned, so we have plasma in this chamber, and we can use DC plasma for metal deposition. And for insulating material, we have to use RF plasma. So the basic process is that the high energy ions strike the target here, containing the material, for example, aluminum, to be deposited. And the excess energy of the ions also aids in increasing the surface mobility. The pressure is normally higher than evaporation. So last lecture we talked about evaporation. It is a very low pressure chamber. So it should be less than 10 to the power minus 5 torr. For sputtering chamber, it is about 1 to 100 millitorr. It is much higher than the evaporation chamber pressure. So because of this high pressure and some other problems, so we can produce very high, very good step coverage. So you can imagine the pressure is higher, and also we have this larger source surface area, so you can have better step coverage. And we're going to discuss in details shortly. Here we show the process of sputtering. So for sputtering deposition, so firstly we have plasma, and plasma will provide ions, normally argon. And the ions, so here's the argon, this is argon ions. And these ions will be accelerated to the target, sputtering target, the cathode. And then if we are sputtering the target, the atom of the target, for example, aluminum, will be sputtered and transported to the substrate. And the deposited film or atoms, it will experience a surface diffusion. and then nucleation and film formation. So this is a basic sputtering process. For ions injected onto the surface of subject, so there are several possibilities. So firstly, if the energy is very low, like much less than 10 electron volt, basically the ion will be bounced off the surface or reflected. And if the energy is very high, maybe first let's talk about maybe when energy is less than about 10 electron volt, but it's close to 10 electron volt, and then the ion will be adsorbed to the surface. And next, if we have very high energy, about 5 kilo electron volt, the ion will penetrate into the material, many atomic layer spacings, and this actually is ion implantation with very high ion energy. And the energy between 10 electron volt and 5K electron volt, and this energy for sputtering. So in this case, the ion, synthetic ion, as will transmit to the subject and make some damage on the top of the several layers of atoms. And then this, the crystal, basically, the upper layer, several layers of crystal will be damaged. And then we have atoms will be sputtered. And this is the sputtering process. The whole process, the mechanism of sputtering. And also need to mention, so we can also have secondary electrons because of ion, incident ion. And these secondary electrons can collide to the argon atom molecules, and then more ions can generate. This is an enhancing process. To sputter alloy, we can use the target with the 2 or more different materials. So for example, if we have for one material A with higher yield and a second material B, this is our violet color, and I think it will be low, it has lower yield. So, and we can adjust the material, the percentage, like increasing this material B and then decreasing high yield material A. And then the result is that we have uniform yield. So we have the same yield for both materials, and we can make the change. And this is surface equilibrium. So, and this is advantage of sputtering. So you remember for evaporation, so we don't have such a, we cannot do this process control. So the process control for evaporation is more difficult than sputtering. And this is one important advantage that we use sputtering for alloy. So for evaporation, the material, target material will be melted. But for here, for sputtering, the target will not melt. Will not melt, and there's very slow diffusion mixing in the solid. But for liquid, so the diffusion will be higher. And this can be used to control. This is alloy sputtering. So sputtering has a lot of advantages over evaporation. It has a better step coverage, very importantly, and there is much less radiation damage than E-beam evaporation. And also it is good for producing compound materials and alloys. So it is our important deposition process for silicon-based technologies when aluminum is widely used. And later, with the advent of gold interconnect, actually gold is not easy to use sputtering. So we can use electroplating. And this is another topic. So for aluminum or silicon, aluminum alloy, composition, so we can use this sputtering process. There are also some disadvantages for sputtering. For example, with argon implanted into the material, there can be some plasma damage. And also, the sputtering is good for ohmic contact, but not good for Schottky diodes. So for sputtering, we have our important parameter. It's called sputtering yield. So sputtering yield is used to measure the number, how many atoms can be sputtered for certain number of incident ions. Simply put, so as the sputtering yield is the ratio of number of sputtered atoms to the number of incident ions. So one ion atom sputtered one atom, so the yield is 1. So if one ion sputtered 2 aluminum atoms, so the yield is equal to 2. So normally for sputtering system, so we have yield about 1 to 3. Actually, this is not a big range. So from this figure, we can say this spot normally so like for from here to here, 1 to 3. And we don't show temperature here. Actually, it's not important. And temperature is not big factor for sputtering yield. So if we keep increasing the temperature, and there might be higher yield. That's because that is because actually evaporation happened. And from this figure, we can see there's a threshold energy. It's about 10 to 30 electron volt here. So below this energy, this threshold energy, there will be no sputtering. So we must have energy greater than 10 to 30 electron volt for some certain materials, and then we can have sputtering. And then the yield will increase. And increase, and then when it reaches about 300, continue to increase to about 1K electron volt of ion energy, it will not continue to increase. The yield will actually will not continue to increase. So some factors, several factors affect the sputtering yield. Firstly, the mass of ion and target atoms. And secondly, we have ion energy. So from the last slide, we can say if we increase the ion energy up to 1,000 electron volt, the yield is increasing. And it also depends on the target crystallinity. Another factor is the angle of the incident ions. The ion incident angle can also affect the sputtering yield. So from this figure, we can say when the ion energy increase to up to like 1,000 electron volt, the yield will keep increasing. Yeah. If we keep increasing above like 1,000 electron volt, there will be too many collisions. Actually, the ion efficiency become lower and the yield is lower. And this figure shows the yield as a function of angle. It's an angle, the ion incident angle, with respect to the normal, the norm. So around 60 to 70 degrees, we have highest yield for this. And then if we keep increasing, so theta equal to 90 degrees, or it's horizontal in horizontal direction, so yield will become 0, of course. And then if theta here is normal to this surface, and then the yield is low. There are some certain number of yield, but the yield is not that high. At about 60 to 70 degrees, and it has highest sputtering yield. And this figure shows the yield as function of ion atomic number for 45K electron volt. So we can say if their atomic number increase, atomic mass increase, and so it will increase, their sputtering yield will increase. So this is our weak function. It is a weak function of ion and target atom mass. So angular dependence, as I mentioned, it is about maximum at around 60 to 70 degrees. So here we show yield is proportional to atomic mass of gas, or like argon, and over atomic mass of a target, time ln E over E. E, this is ion energy, and 1 over cosine theta. Theta is the number, is the angle. And again, this shows their angular dependence of yield. So based on what we discussed, the deposition rate, RD, is proportional to ion flux to the target, so J ion. And it's proportional to the yield. Of course, the higher the yield, the higher the deposition rate. It's also proportional to the transport efficiency. So typically, we assume this transport efficiency is 1. So like for very closely spaced system, so the two, the top and the bottom electrodes are very close. The spacing is very small, and we can assume that the transport efficiency is 1. And then we have a factor for number density. Number density is basically rho over m. Rho, that is the mass density of the target material, and then m is the atomic mass, the mass of a single atom, not per molecule. Per molecule, we typically use capital M. And we are going to have an example to show, to calculate this deposition rate. And the flux J equal to square root P squared over 2 pi chi Tm. So we are going to use this equation. So P, this is the pressure, chamber pressure. And K, Boltzmann constant, T, their system temperature, and M, this is their mass, atomic mass. So the ion density, or in other words, so in the chamber, their ion, so the ionized atom, it actually is very low. So we have argon gas, so some will be ionized, and this number is very low. This rate is very, very low. In a normal system that we discussed, so it is about 0.001%. It's very low, extremely low. And we want to increase this density, ion density, and to increase the plasma, the sputtering rate, and the deposition rate. So we can use a high density plasma sputtering. So mostly we just use magnetron sputtering. Yeah. So the basic idea, we just apply a magnetic field, so like here, and then the electron move, and it will be, the direction will be bending. And then, so it will stay longer in the chamber, and it will generate more ions. So in this way, we can increase ion density. So this is a simple planar magnetron sputtering system. So here we have for, so T, this is the target, and P means plasma. And then here M, this is a magnet. And so we have like, you can also see here, it's a magnet, south, north, south, right? South pole, north pole. And we have north pole and a south pole. Yeah. So the flux, the magnetic flux will go from north to south. And basically we have some sorts of parallel flux. And this flux, this magnetic field, so will bend the travel of our electrons. And then electron will stay in the chamber longer. And then we have a higher ion density. And this, by using this method, we can have improved ion density to about 0.03% versus the normal system of 0.001%. It's much higher, like 30 times larger. And we can even make it greater, like 100 times larger. This is to use high density plasma sputtering to increase their ion density, and then to increase their deposition rate. So for high density plasma sputtering, so we can say here we have the deposition rate as function of pressure, the chamber pressure. So we use high density plasma, and we can use lower pressure, so 1 millitorr, instead of 100 millitorr in non-magnetron plasma, non-magnetron sputtering. And then deposition rate will be increased and pressure decreased. So for film morphology, we can use the zone model. You look at here. So in this figure, we have the temperature normalized to this melting temperature of the target material. And then here we have the pressure, increase the pressure, and or lower the atom energy. So here in this region, we call it zone 1. At this region, we have the lowest energy and also lowest temperature. So in this part. So this part, the film is has a characteristic amorphous, highly porous, and with low mass density. This is because of the low atom mobility of the green film. And then we increase temperature, so increase temperature, or lower the pressure in this way. So then we have this zone. So this zone, we call it T zone. And in this zone, you can see the greens are smaller. And it has a very flat surface, specular surface. This is the zone mostly desirable for operation for some microelectronic applications. So this T zone. And then, so we can increase the temperature or the energy, and we come to this zone 2. In zone 2, there are tall, narrow columnar grains that grow vertically from the surface. And then we continue to increase this temperature and or the atom energy, and then we come to this zone 3. So in zone 3, there are large 3D grains. So meaning there's bulk diffusion in addition to the surface diffusion. So in general, so we prefer this T zone. We use T zone for microelectronics fabrication. And the zone depends on the temperature, depends on the pressure and the energy of atoms. So step coverage is an important parameter to evaluate their deposition. And for microelectronic fabrication, and most time we need good step coverage. So because we deposit metal interconnect layers, and we want the conformal connection. So compared to evaporated film, because we have high pressure and we have high energy of the deposited spaces, so we have better step coverage, even at lower temperature. So this shows the comparison between the smaller source, a point source, and a larger surface source. So for smaller source, so we can say the angle is distributed in like a circle. So in one circle. And then in comparison, if we have a larger source surface, so we are going to have for a wider arrival angle distribution. So there are many different angles of distribution. So this actually contributes to the good step coverage. And this is mostly for sputtering, and this we can imagine this for evaporation. Evaporation, the source is very small, and for sputtering, the source area is very large, and it has different angles, and then it has better step coverage. To improve the step coverage, we can improve the subject temperature, and this will increase the surface diffusion. And by increasing the surface diffusion, we can dramatically improve the step coverage. But the problem is that we have larger grains, and we have inter-diffusion effects for different materials. So another method is to apply a bias, substrate bias. And by applying this substrate bias, so we can redeposit these materials and make their coverage more uniform and to improve the step coverage. And it's shown in this figure. So if we apply a voltage here, the argon will be attracted to this metal film, and it will this is like our sputtering and the deposition process. So this is redeposition of their target material, and it will improve the uniformity of their metal connection. So you can also use a collimator. So in this figure, we show here the wafer, and here the target. And from the target, we have atoms like aluminum atoms. So they will travel in different directions. And for small feature size and for larger aspect ratio, and we want that these atoms travel normal to this surface to get a better deposition along their high aspect ratio layers or patterns. And then we use this collimator. It will only allow these atoms normal to their surface pass through, and this will improve step coverage. So this is for smaller feature size and a higher aspect ratio. Yeah, we use a collimator. Okay, so as I said before, so we are going to have an example. So here, this example is from the textbook. Let's say, yeah, so just write on the board here. Stop sharing. Example 12.4. So this example is based on example chapter 10, example 4. And we want to use a sputtering system. So this sputtering system is similar to the plasma edge system in example 10.4. So I go here. This is a chamber. And we have our something here. Maybe I go here. So this is the aluminum. So aluminum target. And then we have our so this is silicon, this is the wafer. And then the wafer has D, the diameter, 200 millimeter. And then here also, so we have our wafer, D equal to 200 millimeter. So this one is connected to RC signal, grounded, and then actually this is here connected to the aluminum target, and this one, this chamber is grounded. So I list some basic parameters. And here's an ionization rate. So here's the plasma. So ionization rate is usually is low. It's suppose here 0.01% or 10 to the power minus 4. And we also know that the plasma power is increased enough to obtain 0.5 volt between the plasma and the grounded chamber. So V1 equal to V plasma minus V electrode. So probably we just write as V chamber. So this is 0.5 volt. And V2 is equal to V plasma minus V electrode over the target. So this is the electrode or target. And based on example 10.4, and this is V2 equal to V1 times 1047. So we can calculate V2 with this 1047 volt times 1.5 volt. Okay, so we can calculate this is 523 electron volts. So this is the plasma voltage minus electrode, here the electrode voltage. And then the argon will gain, here's the float. So argon will gain energy E ion with 523 electron volts. So for these ions, argon, okay, let's say. And then we want to find the yield. So yield, I like to use Y instead of S, or you can use S. So we want to find the yield. To find the yield, we use okay, I'll use here. Okay. Here. Yeah, we can use this one to find the yield. So this figure is for sputtering yield. And the energy is 523. So about here, 523. And then this is for aluminum in argon. So aluminum, so we just find here, maybe some here, is about 1.2. Okay. So yield is 1.2. So we get E equal to 1.2. And then we have for deposition is RD equal to J ion times S times ET over rho over M. So this is aluminum, and this is aluminum. And S here basically just we write as S. So S equal to 1.2. So this one ET, so we suppose equal to 1. Normally, so we suppose it's equal to 1. And then we have J ion. So we need to calculate J ion, the flux of ion. So J ion equal to square root P squared over 2 pi K T M. So M, this is I. So P, the pressure, so equal to, we know the pressure here, the chamber pressure is argon, total argon pressure is, so from example 10.4, that is pressure is 10 million. And then we only have 10 to the power minus 4 or 0.01% ionized. So we need to multiply by 10 to the minus 4. This is the partial pressure for the ions. This is ion pressure, not the whole pressure, only ion pressure. Okay. And K, this is the Boltzmann constant. And the T, the temperature is given. It is 250 degrees C. And here we have the ion. We need to find the ion atom atomic mass. So M, argon, so this is 40. And then M lowercase m argon is 40 over N0. N0 is Avogadro's number. This is 6.022 times 10 to the power 23 particles per mole. And here we have unit of gram per mole. Okay, so now we know this one. We know all the parameters, variables, and now we can calculate. So it is J ion equal to 2.4 times 10 to the power 2.4 times 10 to the power minus 19. And 14. Here's plus 14 per square centimeter per second. Is J ion. And we have a J ion, and we have a U, and have ET equal to 1. Now we need to calculate the rho aluminum. And this is a mass density. This is a number density of aluminum. So rho Al aluminum, this is 2.7. So 2.7 gram per centimeter, per cubic centimeter. And M aluminum equal to capital M aluminum over N0. And this 27 gram per mole. And Avogadro number that's 6.022 times 10 to the power 23 particles per mole. Okay, so we have all the numbers, and we can find the deposition rate. So the deposition rate is found to be 2.9 nanometer per minute. This is the deposition rate. The deposition rate is not that high. So we didn't consider the magnetron plasma. If like we use high density plasma, so we can improve, remember, 7 times of our times of this deposition rate. Here's some questions for this example. Okay, maybe I should quickly show you here. So. So maybe you didn't see this one. So actually, I find the sputter yield from here. So 523 electron volt from here, and this is in argon ions. I think we found aluminum, and it is about 1.2 atoms per ion. This is the year. Okay, so if no questions, we are going to see you on Friday for chemical vapor deposition.